The last topic in this section is eddy currents. Now, eddy currents are going to seem a little more complicated, but it's following really the same ideas that we're talking about with everything else. And in this case, we are now pulling a big metal sheet. And now it is going to be in a non-uniform field. So again, for the sake of simplicity, we're going to say that this is a non-magnetic metal. This is any conductor. If this was iron, well, you know that the iron is getting stuck to the magnet. So that's why we would think about this being aluminum or copper. Something that doesn't actually get attracted to the magnet, but it's still a conductor. You'll still have eddy currents. The non-uniform magnetic field is really important. For the sake of simplicity, we're going to normally have a region of magnetic field, and then we'll say outside of that region, it's 0. So notice that in this case you have the pole of two magnets, and it goes out of north into south. So you can kind of think about there being this magnetic field here, right? And it's 3D, so I'm trying to draw it further back, but obviously three-dimensional drawing is really hard. So that's like back further. So we would say that there's some sort of region of magnetic field inside, and then outside we would say B equals 0. So in this case, non-uniform could mean changing in a really complicated way. We are typically, for the sake of calculation, going to say a region where there is a uniform field, and then a part of a region where there's not. So we don't say that there's uniform field everywhere. And again, that is actually really important. There can't be a uniform field everywhere. The final ingredient that's really important is the metal is moving. So this is why it's in the section that has to do with moving conductors. It's a conductor and it's still moving. So again, there has to be some sort of force that is pulling it. We're going to have a magnetic force that actually opposes that, but we're not going to talk about that right yet, but keep in mind that there actually has to be a force pulling it. So the whole point of eddy currents is that current is being induced in these loops. Thinking through the directions here can be pretty tricky, but let's try it. So notice that, again, the whole bar isn't in a magnetic field. It's really only the central region. So let's try to block off this region as the part that is moving through the magnetic field. And again, remember which way our magnetic field is facing. It comes from north, right? So let me do that in blue, right? From north to south. So that's kind of downish on our picture. So do V cross B. V is to the right, B is down. What does that mean? You again get a force that's going to separate our charges. And so that's like you're getting this plus side up here and this minus side down there. So that is literally what we talked about in the first video. This is just a moving conductor giving us a separation of charges, but we're thinking about it only in the very middle of this larger sheet of metal. So we've gotten the separation of charges, but there's all of this metal around it. So instead of needing to ride a small conductor on a rail for the current to flow, instead, this then can just loop around, right? So you get these current loops, that's what's in purple, which is simply then those positive charges basically recombining with negative charges. So these are the mechanisms, right? So this is basically current loops, but they're not confined to a wire. They're actually just in the rest of the conductor. So that's what's happening here. So then on the inside, let me clear this off so it's a little more clear. So on the inside, your current is actually flowing that way. Well, then when you do I cross B, again remembering that your B is down, you see that there's going to be a force to the left. So there is a magnetic force acting on the metal due to your induced current that opposes your pulling force. So once again, you can be pulling it and actually have a constant velocity due to an induced magnetic force, but the most important thing here to understand is the shape of these induced currents. So again, it's like there's a region on the inside that we would separately think about, and you would get a separation of charges like the first case, but then those charges are free to flow in the outside regions where magnetic field isn't necessarily changing, or sorry, where it's not moving in the magnetic field. We can think about the magnetic field being zero in these outside regions. So please think through this. Again, it's very complicated to draw. It's really hard to draw from the side. So normally we would do a top-down view, or if you're a really good artist, you can try this 3D angle view, but I would typically do a top-down view. So you would think about your magnetic field in this case being like into the page. Okay, so eddy currents are cool because I can hand you a device where this happens and it will just feel weird to you. So we'll do a quick demo in class that's pretty cool regarding this. And one of the nice things about it from a physics class point of view is you really have to understand what's going on here with many different forces, magnetic fields, and currents. So there's a lot of rich physics to think about. And again, draw pictures in this case. Draw multiple pictures if you have to. But finally, this actually has some really important applications, and that has to do with braking. So one of the cases that the book goes through that I'll focus on, though there's other cases where eddy currents are used, is actually braking a train. So you can imagine that a train has a lot of momentum. And so if you want to slow down a train, you could imagine taking brakes, like how they work in a normal car, and just pushing an object against the wheels to cause friction to make the train slow down. But clearly that's just going to really grind away pretty quickly at whatever you're pushing against the wheels. So instead, you can actually do electromagnetic braking. And in this case, what is on the outside here is part of the train, and it's an electromagnet. Inside is the rail, right? You know that trains ride on rails, and rails are metal. So what you can do is basically have this electromagnet that is straddling the rail, and that normally is off. When the train is moving, the electromagnet, and remember that electromagnets are just coils. So you have this coil that's straddling the wire, but if it's off, it doesn't matter. If it's off, nothing happens. But then you turn a little bit of electricity in, you get a current flowing, which then creates this magnetic field, right? So effectively, this is a solenoid here. You create this magnetic field that goes through the rail. Now you're getting eddy currents. So before we have this magnet up down, now the magnet is in orange. It's straddling the rail. Before we were pulling this metal sheet, now the train is rolling along the rail, so the rail is being pulled effectively through this magnet. That means that there's going to be this opposing force, right? So we've been talking always about, well, what is the force on the metal? But from Newton's third law, we know that there must also be a force on the magnet. So that's what's actually happening here. There's actually a force backwards on the magnet, equal and opposite from the force that the magnet is exerting on the rail, and that slows the train down. So again, the details of this can be really complicated to think through. I recommend using this picture to think through it. But what's cool is that there are a number of applications of eddy currents. And the book will talk about a few of them. Many of them are pretty hard to calculate. Eddy currents in general are hard to calculate. And so we might focus on some more simplified situations so that it's easier to actually do those calculations.